Tonight she's going to tell us about non-Euclidean virtual reality, and she has a lot of cool demos and toys, and so if you want to stick around afterwards and come down and chat and maybe give things a try, I think that's a possibility tonight. If you have questions during the talk, please try to hold them until the end, and then Brian and I...
You can interrupt me.
What's that?
You can interrupt me.
Oh, okay, you can interrupt Professor Matsumoto. And then at the end, if you have a question, Brian and I will run around the microphone to you, so just raise your hand and then wait, because it's very hard for the speaker in the front of the room to hear your questions. The acoustics sort of work one direction. All right, without further ado.
All right, thank you, Ed. Well, thank you all for coming out to this public lecture. So I'm a professor here in the physics department. I have a group, and we use geometry to make new materials. So basically, our motto is making materials with math. So I'm going to be telling you about some of the cool things that we've discovered along the way. So currently, I've got students working doing virtual reality, 3D printing. We're looking at textiles, fabrics, knits, things like that. So we have a pretty eclectic group, and I have plenty of my students are here up front, so if you're interested, you can come talk to them afterwards too. So today I'm going to be giving a bit of a non-conventional lecture. So at the beginning, I'm going to tell you a bit about curvature and how you can think about shape and curvature from the patterns that you use to make clothing. And then from there, we're going to take that idea, abstract it a little bit to make it more mathematically rigorous. And then from there, we're going to start taking our first steps into understanding what non-Euclidean space is, so what curved space is. So you may have heard things about gravitational waves recently. If you've heard of gravitational lensing, a lot of these phenomenon in cosmology are really based on the idea that space is intrinsically curved. So this is going to extend this idea and try to create spaces that are not physically possible to make. So basically, what we're going to do after that is I'm going to get the virtual reality running, and I'm going to take volunteers from the audience, and we're going to do some exercises with the virtual reality to try to give us a gut intuition about how curved spaces work and what sorts of phenomenon you would see in curved spaces that you just don't see in regular old everyday Euclidean world. Okay, so to begin with, we're going to talk about curvature. So curvature is a geometric principle that's very near and dear to my heart. But let's start out with something really, really simple. I mean, we've got Marilyn Monroe in this beautiful flowy dress, but we're not going to start quite there. We're going to start with something a little more simple. So we're going to start with making a man's dress shirt. Okay, so, I mean, I guess everyone here is wearing clothes. How many of you have ever thought about what sorts of pieces make up your clothes, what this would look like before it was sewn in? Okay, so I see maybe 10% of you holding up your hands. So I'm going to show some of the rest of you what this might be like. So, I mean, you might think, okay, well, I've got a t-shirt. It's clearly just got two pieces of fabric cut out like this, and I sew them together, and I'm good to go. But if you actually look at the pattern that's used to make this dress shirt, you find that you get this ridiculous, crazy thing. And if you look at these, so there's a fold, which gives you the only straight line in this entire piece. Everything else, you have all of these intricate little bits, folds, zigzags, curves. All of these shapes are there to take something that is flat and construct it into a curved surface. Like, no matter how skinny you are, or you think you are, you have curves. Every human body intrinsically has a curvature to it. And it's impossible to take something flat and wrap it around a curved surface without either adding curved lines or, as we're going to look in a second, what happens when you add seams. So this is an example of something that's very commonly used in shaping women's wear. I guess I don't have any darts on this dress, but most women's clothing have what are called darts. So you take a little triangular fold and you sew it off. So what happens is that instead of laying flat, you find out that the fabric has folded up into this conical shape. So here's the little point of the triangle, and then the rest of it is hidden inside this fold. So this is something that we use to make what's called positive curvature. So we're removing a little bit of area and we make positive curvature. So this is maybe a little counterintuitive, but just bear with me on this. Okay, so what happens, this is something you can see in my skirt here. So I've got this sort of ruffly tulip skirt. And this is something that you see here. And these things are called godets. So this is kind of the anti-dart. So I take an extra wedge of fabric, I slit open a seam on my skirt, and I sew that in. So instead of taking area away from my sample and from my dress, I am now adding new area into that. So this is something that's going to give you what's called negative curvature. So this is going to be something that's like a saddle. So my skirt here, it curves out down here, but in along this direction. So this is something that has what's called negative curvature. Things that have positive curvature are things like the surface of the sphere. So it's bending down in both directions, or from the bottom, bending up in both directions. All right, so here I have, let's make this a little more precise with fabric. So here I've got this lovely fabric that has a honeycomb pattern on it. And I have cut out exactly 1/6 of this pattern. So I have 60 degrees here and 300 degrees around here. And then what I'm going to do is I'm going to join this edge to this edge with a seam. So I get now this conical shape where I've taken out exactly 60 degrees of angle surrounding this point. So that's one way we can measure curvature, is by looking at the angular deficit around this point, so how much angle we've taken away. Okay, so now I've got this extra wedge of fabric. So what do you think I'm going to do with it? Okay, I'm going to stick it into another piece of fabric. So I'm going to take this, cut it open along here, and put this in and see what we're going to get. Okay, so now I have this perfectly regular hexagon in the middle. So this had 360 degrees around this point, and I'm going to add in 60 degrees. So that's going to give me something with 420 degrees. And when I do that, I end up with this structure that's all ruffled. So this is something that cannot lie flat in the plane, no matter how hard I try. I can sort of smooth some parts out, and that looks flat, but then I've forced it to bunch up somewhere else. So this cannot be smoothed no matter what. And some people find this a little bit strange when they're playing with material like that. They'd like to be able to neatly fold it up the same way you fold up your t-shirt and put it in the drawer after you wash it. So here's a dress that's based on this idea. So this is called the 567 dress. So it was made by my friend Andrea Shui, who is a clothing designer, and Robin Sullinger, who is a professor of theoretical physics at Kent State. So the idea here is that this dress is made entirely out of these regular polygons. So we look at hexagons, pentagons, and heptagons. And despite how it looks, each of the side angles of these are the same length. The edges are the same length. Okay. So what's going on here is that we can use the number of edges on each of these polygons to control the curvature in the dress. So places where I would have positive curvature, I want to take angle out. So I'm going to use my 5s. So those have a little bit less angle. So I've got a 5 here, and that's going to be part of the bust. So places where I'd naturally have positive curvature. whereas I've got some 7s, so I've got one in the center and a ring of 7s around the waist. So these are there to add in extra angles. So these are going to sort of let the material flare out, and this is going to give us something with negative curvature. So we can use this idea of adding an angle or taking away angle to prescribe curvature to a garment. Right. Okay, so what do you think these things have in common? So I've got this beautiful couture wedding dress and this jumble of human intestines. Does anyone have a guess? They're curved. Okay, that's a definitely true. But would you believe me if I told you that the mechanism that the physical mechanism that causes this wedding dress to ruffle, the tool in the skirt to ruffle, is exactly the same as the mechanism that causes every human intestine to ruffle? I mean, there's a reason that if you looked at my intestines, the wiggles in them are going to be roughly the same as yours. It's not like someone took a rope and just jammed them inside our abdomens. There is a pattern to it, and the pattern has everything to do with this particular type of elasticity. Okay, so both of these have negative curvature. So let's look at this mechanism. So this is what happens in the dress. So I take a stretchy piece of material that's cut short, and I've got a long piece of a stiff material. So in this case, it's called boning in a lot of textile applications. So it's this sort of thick, stiff, but still curvable material. And what I do is I'm going to take this stretchy material, I'm going to stretch it out as wide as the boning, and I'm going to sew them together. So I've got a huge amount of strain in my material, but there's this constraint that it has to be as long along the seam as this top stiff piece of fabric. And what happens is it relaxes, is it buckles out of the plane into this beautiful, regular, ruffled pattern. So this is what makes up the skirt. So it turns out that human intestines grow in a very similar way. So what happens while you're developing, while you're an embryo, is that you've got a gut tube, which is what's going to become your digestive tract, and you've got a neural tube, which is going to become your spine and your back, and your spinal cord. So what happens is that there's actually a membrane that connects your gut tube to your neural tube. So this very thin membrane that connects them. And what happens is, as you grow, is that your gut tube grows longer and faster than your spinal tube, than your neural tube does. And what happens then is the material that's going to make up your small intestines is growing faster than the membrane that's connecting it to the neural tube, and it's forced because of geometry and elasticity to ruffle and form these very regular wiggles with negative curvature. So we do see, negative curvature in a huge number of physical systems. So this is a micrograph of the mitochondrial membranes inside the retina of a tree shrew. And this forms these beautiful, intricate, what are called triply periodic minimal surfaces. So this texture forms entirely naturally. It self-assembles, and you can get this to form in a lot of systems. So this is entirely based on the geometry of the molecules. At a larger length scale, soap films try to minimize surface area. And it turns out that that naturally leads them to have these saddle-like structures. So here is just a plain little saddle here. But on this side, this is a framework that would give us a triply periodic minimal surface. So the soap film that spans this should be exactly the same as one of the structures in the mitochondria, in the I mitochondria. And then we know that the universe is curved. We don't happen to know at the largest scales what the curvature is. It seems like it's pretty flat, but this is still an open question since we don't have any information about the boundary yet. Okay, so we also see this idea of negative curvature in nature. So we've got in the top panel here, this is a nudibranch that's swimming. So this is a marine invertebrate, and it's got these ruffles that are running down its mantle, and those traveling waves it uses to propel itself. So it can change the frequency on one side and turn, and so on and so forth. You see it in things like coral and kale. So what's going on here is that the plant wants to maximize, or I guess coral's an animal, but it wants to maximize the surface area that is accessible to resources. So it's going to do this by ruffling and bending, and this is going to give you, again, negative curvature. And the calla lily, that's my favorite flower, so I figured I'd throw it in for kicks. Okay. So now we're gonna switch gears a little bit and try to make some of these notions coming from clothing design, coming from biology, and make them a little bit more mathematically rigorous. Okay, so what I've got here are 3 of the 5 Platonic solids, and these are ones that are made only with triangles. So I've got a tetrahedron, which is made out of 4 triangles, but if you look at each vertex, there are 3 triangles around every vertex, and every vertex is the same as every other vertex, and this is what makes it a Platonic solid. Here I've got an octahedron, and the only difference between these is now each of my vertices has 4 equilateral triangles around them. Let's see. And then on the far right over here, I've got an icosahedron. So this has 5 equilateral triangles around every vertex. Okay, so what happens if I do 6? What do you guys think?
6 triangles?
Yep, 6 triangles around every vertex.
What do you want? It's a sphere.
Is it going to be a sphere? What do you think? It'll be flat. Okay, so let's see what's going on. So, I'm going to skip that. So if we have 6 triangles, we do, in fact, end up with something flat. So this is a regular triangular packing of space. The circles in here make a honeycomb lattice. So I've got, let's see, do I have? Well, this is squares. There should be one somewhere that's triangle. Oh, here we are. So I've got this guy. It has 6 triangles around every vertex, and so it's flat. So let's continue this pattern. What happens if I put 7? So I've got another little doily, and I can get 7 triangles. You can verify that there are indeed 7 triangles around every single one of those holes. You verify? Okay, excellent. And then I can do the same thing with 8. And you'll notice these get more and more ruffled as we go. So getting back to what this has to do with curvature. So tilings are sort of ways of fitting regular structures onto surfaces. So if you imagine I take my tetrahedron, I put a balloon inside and sort of inflate it out to the surface of the sphere, I will get something that tiles the sphere. So this is what would happen if I did this with the icosahedron. So I have a triangle, this sort of weird curvy triangle here, and there's, notice, 4 weird curvy triangles that meet at every vertex. So this is a tiling of the sphere. So we discussed that this tiling with 6 triangles around every vertex, that gives us a plane. But what about this? I mean, I've got this model, They're really ruffly. I mean, I can go on for a while, but at some point I'm going to get stuck. This is not something that intrinsically can fit into our Euclidean space. In fact, there's a theorem that you cannot embed the entirety of this structure into Euclidean space. So what is this? So let's think for a second. So this is something that's called the hyperbolic plane. I told you that you can't fit it in all of Euclidean space, but then I've got this drawing right here. This looks like, hey, bam, I've got it. I can draw it on the board. We're all good. But let's think about maps for a second. So maps from a curved surface to a flat surface always introduce distortion. So we're pretty familiar with this idea of the Mercator projection here. This is the standard high school, elementary school map in your classroom. And you'll notice that Greenland here is maybe a little bit larger than Africa. And if you look at the globe, on the other hand, here's Greenland and here's Africa. You can fit something like 7 or 8 copies of Greenland inside Africa. I forget the exact number. But this is just showing you that anytime I take some curved object and try to smush it down onto the plane, I'm always going to introduce distortion. So the same way we've got Mercator projections and all sorts of other types of maps you might find. Like there's now a new, more geopolitically correct map that tries to keep the area of the countries as close to what they actually are in real life. That's something that there's a movement to put that into schools now. We'd like to do the same thing with this hyperbolic plane. So this is the most common map of the hyperbolic plane. This is called the Poincare disk model. And here is one of the triangles. So if I follow this around, I've got a triangle here, and a triangle here, a triangle here, 4, 5, 6, 7 triangles. So this is indeed this case where I have 7 equilateral triangles that meet around every vertex. But you'll notice this doesn't look like an equilateral triangle. This is kind of stretched in some weird ways. I have 2 straight lines and 1 curved line. This is kind of a funky looking triangle, but this is the distortion that's coming from the map. I've got another map. This is called the Klein model. Here, this looks a lot more like an equilateral triangle. I'm happy that the edges are straight, and this is where the distortion in these screens might come up, but if you look closely, you'll notice that these angles are not 60 degrees like you would expect in an equilateral triangle. So here we're getting angular distortion, but we're keeping straight lines straight lines. So no matter what model you choose, something's got to give somehow. There's one more. This is called the upper half-plane model. I'm not going to go into details, but there's this lovely print by Henry Segerman and Saul Schleimer that shows how all of these different models are related to one another. So this is a model that's on what's called the hemisphere model. If I take a light at the North Pole of that and look at how the light rays pass through it, I get a projection down here. This is my Poincare disk model. This is the first one we saw. The second one is generated by taking the light source and moving it infinitely far away, like the sun, and projecting straight down. This gives us the Klein model as the second model. And then if I put a light at the equator and cast it on the wall, this is the last model, the upper half-plane model. So these are models you might have seen before. How many of you are familiar with this artwork? Okay, so there's a number of you. So this is circle limit 4, I think. This is a lithograph by M.C. Escher. And what M.C. Escher wanted to do was he wanted a way to see infinity. So he had a conversation with the mathematician Coxeter, who told him about this notion of the hyperbolic plane and the Poincare disk map. And he's created this, this beautifully intricate, interconnecting series of demons and angels. So let's have a closer look at this. So I've got 3 demons in the center interlocking with 3 angels. Now let's look at their wingtips. So I've got wingtips that meet along here. So I've got 6 figures going across. And then let's look at each wingtip. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 figures that meet along each wingtip. So what's going on here is that you're supposed to imagine that this demon in the center here is exactly the same size and the same shape as this demon up here, and this demon over here, and this little tiny guy in the corner right there, if I could hold my hand steady enough. And that takes quite a lot of imagination. So let's look at this again. So if I look at these places where all of the wingtips meet, I can inscribe a circle around each of those points. So what I end up with is I have a circle, and I have 4 other circles meeting it at this point. And as I go around, there are boundaries with 6 circles around that. So what we'd like to do is we'd like to be able to see what it would be like to live inside this space. So see what it would be like to be an ant that's walking around in this infinite space. And the model we're going to choose is going to be a little bit different from this, but it's got a similar idea. So here I've got sort of these hexagonal circle bits that meet 4 around every vertex. I'm going to swap that for here I've got squares that meet 6 around every vertex. And so I've got a blanket here, which is the same layout of what you might see there. But here I've taken it and I've tried to keep all of the edges the same length and all of the squares the same size. So in order to do this, I have to push things out of the plane. They're going to become very ruffly. But all of these models, looking at the blanket, looking at the Escher lithograph, looking at the 3D print, all of these are models from outside the hyperbolic plane. We really want to see what it looks like inside. And so this is where virtual reality is going to come in handy. So we're going to do this using one principle. We're going to say that light rays should follow geodesics. So let me unpack that for you. So you can imagine in our space, the way I see things is there's a photon that is coming out of the projector. There's one that's going to intersect my eye. It's going to excite some molecules in my retina. My brain processes that, and I say, oh, there is some light coming out of the projector. So when the space is curved, we still want photons to do the same thing, but they're going to follow a different principle. They're going to want to follow the shortest distance between 2 points. So we can think about this from the point of view of a globe. So the shortest distance between 2 points is part of a great circle. So this is why if you're flying from San Francisco to New York, it seems like you're going very much further north than you would expect. Or if you're going to certain places in Europe or Russia, you might end up flying over the North Pole, depending on where you leave. So in curved spaces, light rays have to follow these lines of shortest distance between 2 points, and these are called geodesics. So this is what we're going to do. So in order to create a virtual world on our computer, we need 4 components. So I'm going to need a model of the space. So I'm going to need a way to associate every point in my space to a number in my computer. I'm going to need a way to draw those points on the screen. And this is this principle that light rays must follow geodesic. So this is telling me that if I want to look at an object up there, you can imagine there is a straight line in my space or a curved line in curved space that's the shortest distance possible going from my eye to or from the projector to my eye, I guess makes more sense than me shooting light beams out of my eyes. I want a way to move around. I want a way to move around this space. And so I've got some pretty nifty equipment here. So I'm gonna be using the HTC Vive. So what you'll notice are I've got these funny towers on my tripods. And those are called lighthouses. And what they're doing is they're constantly sending out signals so that my headset knows exactly where it is in space. So it's going to allow me to walk around in the space and really accurately track where I've moved. And then lastly, I need a set of landmarks to help the user navigate space. I mean, I could put you in there in a black screen and tell you, this is curved space, but you wouldn't believe me. You'd say, well, your Hello World program broke. So we're gonna do this, and we're gonna do this with tilings. So the first space we're going to do is we're going to do a space that's called, mathematically speaking, it's called H2 cross E. So this is gonna be what would happen if I took this blanket, made it infinitely large, and then extruded it into the z direction. So this is like I'm taking the entire hyperbolic plane in the xy direction, and then it's just normal, regular Euclidean space, up and down. Okay, so, see, I think I'm gonna skip this. So let's see, this is the time for my first demo. So let me switch over, I'm gonna switch over to this screen. So for all of the demos, I'm gonna want some audience volunteers. So please keep that in mind. I think I'm gonna take 2 for this, and then I think there's probably room for 4 or 5 volunteers. And we're basically gonna spend the rest of the time talking about how to use your body to move around in these hyperbolic spaces. So who can I get to be my first demo? My gosh, there's a lot of people who are excited. So okay, you in the gray sweatshirt. Oh, sorry, there's 2 of you. I guess yes. Sorry, so what's your name? Jesse. Okay, fantastic. So what I'm gonna ask you to do, Jesse, so I'll have you put on the headset, and I'm gonna have you stand right here. And I'm gonna narrate what you're gonna do. So this is gonna be, I'm just gonna have you, so these are, so the idea is that we are in a space that is squares, but this is a weird space where there are 6 squares that meet around every sort of vertical pole. So I'm gonna have you sort of walk through that and try to show us that, but I'll narrate through what you're gonna do. All right. Looks like it's a little loose. All right, so I'm gonna put my hands on your shoulders and sort of put you into, okay, perfect. So right now you're just seeing she's seeing something that's a lot cooler than what you guys are seeing. Right now she's seeing the sort of lobby of Vive World. So what I'm gonna do is I'm gonna put her into now this is H2 cross E. So I'm gonna have you look straight forward into that sort of blue sort of octagon in front of you, so into this. And you're gonna just walk forward, just straight forward into that. So I will make sure you don't crash into anything. Okay, stop there, and can you take like a step back so you're just in the center of that sort of blue room? Okay, so Oh, don't put your hands over it. Sometimes it loses tracking. So look straight down. So just for everyone, looking straight down, everything looks kind of normal straight down, but if she looks side to side, everything looks totally different. Okay, so, okay, so now turn 90 degrees to your left, Jesse. So me. Okay, so now you're looking into the sort of light green room. Normally I give these sort of ice cream cone names, so I guess this is the mint chip room. So you can walk straight into that. Okay, stop and turn 90 degrees to your left again. So now you're going into the rainbow sherbet room. So you can walk straight into that. Okay, now turn 90 degrees to your left again. So now you're going into the strawberry cheesecake room. Okay, so that's the I guess, fifth room she's gone through. So if this was Euclidean space, she'd be back where she started. Okay, now she's gonna turn, I guess, 90 degrees to her right again, and you're gonna look into a dark red, oh no, you're, me rotate you. Turn 180 degrees around. Okay, so now you're, now you should be facing a dark red room. Okay, so the dark red cherries and chocolate room, you can walk into that. Oh, sorry, the thing's caught around your foot. Okay, perfect. Okay, and then turn 90 degrees to your left again, and then walk into the Black Forest cake room. Okay, and then turn 90 degrees to your left again, and you should be basically looking at what you started when you first walked into the space. So take off your headset and see where you're facing. So, so you started out, so for everyone, Jessie started out standing where I'm standing, facing you guys, facing the audience. And what she did is she walked around in this big circuit and ended up standing here, facing away from you. So thank you so much, Jessie. Okay, so let's have a little look at what Jessie did, sort of from the top-down perspective, not from the her eyes perspective. So this would be Jessie here, and this is what she would see if she wasn't busy looking around at all the cool stuff in there. So this is an animation. So she first walked into the blueberry room, and then turned 90 degrees to the left, walked into the mint chip room, turned 90 degrees to her left, walked into the rainbow sherbet room, walked 90 degrees to her left, walked into the strawberry cheesecake room, turned 90 degrees to her left again, walked into the cherries and chocolate room, turned 90 degrees to her left again, walked into the Black Forest cake room where she started, turned 90 degrees to the left again, and she's looking at the blueberry room again. So you'll notice in hyperbolic space, she would have walked around a complete loop, but you guys all watched her. She started in the corner here, and then walked around, did 6 90-degree turns, and ended up, as one would predict, as it 6 times 90 is what, 540? Is that the snowboarder, skateboarder trick? So she turned as many times as you would expect in Euclidean space, and these two things don't match up. And this is actually a mathematical consequence of living in curved space, is that this is a concept that is called holonomy. So this is something we might be familiar with. So imagine I'm standing on the surface of a sphere. My right arm is pointing to the North Pole. So this is the Earth, say. I'm standing at the equator. My right arm is going to be pointing towards the North Pole, and my left arm is going to be pointed east. Okay? So what I'm going to do is I'm going to start walking. So I walk a quarter of the way around the world. I walk up to the North Pole, and I walk back down. And I haven't moved my arms in orientation, so I'm walking kind of like this. So I'm fixing my orientation, I'm fixing the position of my arms, and when I get back around, I find that I've rotated, so that my right arm, which was originally pointed towards the North Pole, is now pointing to the west, and my left arm, which was originally pointed to the east, is now pointing north. So I've gone around a closed loop on this curved space, and I've come back rotated. So this is what's called holonomy. So let's have a look at what this means for Jessie. So imagine instead of turning 90 degrees, she walked like this. So I guess just keeping her orientation fixed. She's always looking straight forward at you, the audience. And this is what's going to happen as she walks around. So she's facing along the blue arrow, and her right arm is pointing along the red arrow. So she starts here in the first room, walks, sorry. Okay, hopefully that won't flicker at you anymore. Unless it's gonna fall off the desk.
It's outside of the...
Yeah, it should still be able to see this one though. Well, I'll put it on the floor then. Anyway, so she starts in this room and walks forward into the next room, to the left into the next room, backwards into the fourth room, to the right into the fifth room, forward into the sixth room, and backwards into the room she started in, backwards into the first room. And you'll notice that she started facing in this direction, and she ends up facing in this direction. So she ended up coming back as having rotated by 180 degrees. And this is what, in fact, you guys saw. So she started over here facing you and ended up in an entirely different place, but facing the opposite direction. So this is another way of understanding holonomy. All right, so can I have one more volunteer for this space? I think I saw you first. I guess I have to pick from the side of the room next time. What's your name? Lucy. Lucy? All right, so you'll put on the headset. Is that too tight? Okay, so Lucy, you're gonna face any one of the octagonal rooms you like. And do you see, like, you've got a pretty regular octagon in front of you, and through that you've got this like tall, skinny octagon behind that, and then you see this sort of string of skinnier and skinnier octagons. So look at the second one away, and keep your eyes fixed on that and walk forward towards it. So what's happening to it? It's getting bigger. What direction is it getting bigger in? It's widening out. So it's changing its aspect ratio. So do you want to maybe turn to a different side and okay. You're gonna get a little close to the edge, but I'm gonna keep an eye on you. So as she's walking towards you, you'll notice that the aspect ratio is changing. So thank you so much, Lucy. Okay, so let me try holding this. So what's going on is that in this particular space, the horizontal direction behaves very differently than the vertical direction. So the vertical direction is just standard Euclidean space. So we're all kind of used to how distances change. We've got a vanishing point, and as things move away from you, they decrease linearly in size. So this is very prominent in classical art. In this space, we've got something really strange going on. So in hyperbolic space, we've got an exponentially growing radius. So we've got an exponential number of more rooms as you go further and further out. So what's going on is that as you move a short distance, the width between the windows that you see is growing exponentially in this direction, whereas it's growing linearly in the vertical direction. So the idea here is that the anisotropy of the space is giving you this really strange impression that rigid objects are flexible. It's like living in a house of mirrors where the mirrors are fixed, but it makes everything else look like it's changing in size. Okay, so we're gonna move on to our other space. So this is giving us our first taste of hyperbolic space, but after that we are going to, this is full-on three-dimensional hyperbolic space. Every direction you look is hyperbolic in this space. Okay, so what we'd like to do is we'd like to go from this idea of two-dimensional space to three-dimensional space. So in this space here, I have a set of squares, and I have 4 squares that meet around every corner. So this is a standard like floor tiles. So I guess I will tell you what these numbers mean here. So the first one is the number of sides of the polygon, and the second one is the number of polygons that meet at a vertex. So I'm going to take this idea and let's go up a dimension. Let's go into three-dimensional space. So I've got another tiling here. So the first 2 numbers mean the same thing as they do here. So I've got now squares that meet 3 around every corner. So can anyone tell me what shape that would give me? A cube, exactly. I have squares. I mean, I guess I would pick a normal room, but there aren't really right angles here. So in the corner of a normal room, I'd have one wall, another wall, and the ceiling or the floor, and that would give me the corner of a cube. So I've got 3 squares around each corner. And then the last number here is the number of these cells, these cubes, around every edge. So here I've got 4. So you can imagine this is like the standard Minecraft tiling of space. So you've got cubes and you stack them together. And you can create your world that way. So there are 4 cubes you can stack around every vertical edge. So now we're going to go to hyperbolic space. So let's think about how we extend this here. So we've got, this is our tiling here. We've got 4, 5. So this is, the cells are squares, and we've got 5 around every vertex. So this is something that if we took actual squares and tried to fit them in the plane, this would ruffle out of the plane. So this gives us some tiling of the hyperbolic plane. But when we go up a dimension, let's see what happens. So we've got, again, 4, 3 is going to give us a cube, but now we've got 5 cubes around every single edge in this. So it's like we took the Minecraft tiling, and at every edge, we opened up space and we shoved in another cube. And we've done that everywhere in all of space. And we're going to do this again. We're going to make this 4, 3, 6. So this is cubes that meet 6 around every edge. So this is our analog of taking squares that meet 6 around every vertical pillar. And this is this is what's called the Poincare ball model. This is what happens if we take the Poincare disk and move it into three-dimensional space. And we have, here's a cube. I've added another layer of cubes, so those inner ones should have 6 around every edge. And I do it again. And this is just, I don't know, this looks like Sonic the Hedgehog had a really bad hair day. So let's try to understand what's going on in here. And to do that, I've got this beautiful 3D print that was made in collaboration with Royce Nelson. So this is going to be the actual space we're walking around in virtual reality. So the idea is that we've, again, taken cubes, but instead of regular cubes, I've cut off the corners, so I end up with these sort of octagonal windows. And this is just drawing the thickened edges. So this is what our space would look like in the Poincare ball model. So if you hold your eye up right to the center of it, you might start to get an idea of what it looks like, but it doesn't actually substitute for the real thing. Okay, so I'm going to do a bunch of demos in this space. So let's see. I need a volunteer, but I need a volunteer who's willing to be really silly. Okay, you seem super excited about being silly. So come on down. So what's your name? Dean? Okay, so I'm gonna teach you the moves to the holonomy dance. Okay, so this is bad middle school dancing, so you're gonna keep your feet planted to the floor and you're gonna move your head around a lot. All right. Okay, so the first move is gonna be called the hula hoop. So I'm gonna plant my feet, I'm gonna move my head in as big a circle as I possibly can. Okay, you got that one? Okay, the next one is called the TV set, so you gotta, get ready. You're gonna go over, down, over, up. So you're gonna just keep doing that motion. Okay, so this one's the TV set. And the last one is called the bicycle. So this one I haven't tried to do in a skirt, but we'll see if this if I fall over or not. So you're gonna change up your stance a little bit. So, you're light on your feet. And you're gonna go like this. So you're gonna go forward, down, back, up. Okay? Okay, so that's the bicycle, that's the last one. So I'm gonna put you in the headset and get you switched over to three-dimensional hyperbolic space. So put it on like you put on ski goggles. It might be a little tight. Do you want me to loosen it? Let's try that. You got the microphone jack caught. Okay. So you might want to pull it down a little bit further in the back. Okay. Is that comfortable or is that too loose now? Let me tighten it a little bit. Okay. Okay, so I'm going to switch you over to fully three-dimensional hyperbolic space. Okay, so here we are in the sort of standard looking rooms. I'm going to change your view a little bit so you actually are seeing what it's like to live in a cube. Okay, so which was your favorite dance move?
The hula hoop.
The hula hoop. Okay, so you're standing facing a magenta cube. So keep your eyes fixed straight forward, and now do the hula hoop. So remember, the bigger the circle with your head, the better. All right. Okay, stop. So you started out looking at the magenta cube, and now what's going on? You're facing a blue cube. So as Dean's making these closed circles with his head. What he's doing is he's changing his angle with respect to the curved space. So this is holonomics. You can stand there with your feet planted, move your head around, and try to just move space just by moving your head. Okay, so what's your second favorite dance move?
The TV thing.
The TV set. Okay, so let's do the TV set. So now you're facing square on to the blue room. Okay, so now let's try the TV set and see what happens. This one you don't have to go very far to see what's going on.
Yeah.
So now instead of rotating like this, he's rotating like this. Okay, so the last one, the bicycle. So before you start, what do you guys think is gonna happen? Okay, I'm seeing a lot of people doing this, so we're gonna rotate around sort of this axis. Okay, so Dean, give me the bicycle. So this one's a little harder to sweep out area. You're getting it pretty close. Okay, now stand up and see what's happened. So where's the blue room that you were staring at? So it's way up there and rotated around. So this is the holonomy dance, everyone. Thank you, Dean. All right, so we're running a little bit late, so I've got time for one last volunteer. Okay, I saw your hand first. All right. What's your name?
Pargav?
Pargav?
Yeah.
Okay, great. So Pargav, why don't you put on the headset? I think I'm going to tighten it a little bit on this one. Okay, so why don't you turn around to face the audience. Okay, so I'm going to change your view back to the original view. Oh, sorry, can you take a step back? Take 2 more steps back. So you're nowhere near the wall. Okay, so now we've got you sort of zoomed out so you can see this is our original view. So what I'm going to do now is I'm going to change his view so that I remove the pillars in between those triangular windows, and this is going to make it look like he's sort of in some sort of outer space scene with a lot of jewels in it. So find a triangular window and go and stick your head in it. I think I'm getting close to the... Okay. So stick your head all the way inside it. So it looked on the outside, it looked kind of like a regular closed polyhedron. So you can sort of walk around inside there and see what happens. So it looked like this closed polyhedron, this closed icosahedron or something like that. But now that he's inside, he's in this sort of strange world. And as Pargav walks around, he's going to see that the triangles will follow him around everywhere. So would you guys believe it if I told you that this is the Euclidean plane? This is the regular Euclidean space? No? I'm getting some no's. So let me see if I can show it to you based on what we talked about with the triangles at the beginning. So can you, let's see, what's a good place for you to, so take a few steps forward and then turn around. Okay, so Pargav is now look down a little bit. Perfect. So you can see that Pargav is looking at this triangular pattern. So these are the triangles that are made from cutting the corners off of the cube. So these are just regular equilateral triangles. And if you look at the vertex, you can see that there are 6 equilateral triangles. So there's a green one, a magenta one, a purple one, a pink one, a light pink one, and a yellow one. So there's 6 of them around here. And at the very, very beginning of this lecture, we pointed out that there's a tiling of the Euclidean plane that has 6 equilateral triangles around every vertex. So to end, I've got a question for you, Pargav. How do you feel about monkeys?
They're pretty cool.
Okay, so you're not going to mind if I stick you in there with an infinite number of monkeys, are you? No. Okay. So step outside, go back through one of the triangular windows. You can sort of go down and duck. And now there are an infinite number of monkeys. The monkeys have 2 arms, 2 legs, a head and a tail, and they are all holding each other's hands and feet, creating this infinite pattern of monkeys. So thank you so much, Parga. Thank you. All right. Thank you for letting me run a minute over. So the last thing I'm going to point out is these are available on the web. If you happen to have an HTC Vive at home, you can run the full simulation. If not, you can go to these websites on your smartphone and use the gyroscope inside it to look around the space. And if you want to move forward, you just touch the screen. So thank you so much for your attention, and thanks for letting me run over. Oh, and before you all go, I would like to point out that after we take a couple of questions, this is going to be up for, I guess another hour. So I think we're kicked out of here at 8:30 or something like that. So this is around. You guys are free to hang out and try it, play with any of my toys up front.
Do we have any questions for the speaker tonight?
There's a question down here.
Ryan.
So one of the images really looked like we were seeing.
There's a microphone for you.
Oh, one of the images we.
Oh,
Hello? Can you hear me?
I think it's on.
Anyway, one of the images looked like you were really looking into infinity versus the one that you had labeled seeing infinity.
Yes. So.
I didn't see infinity in the one labeled that, but I saw infinity.
Yeah, so that's a great point. So Escher was trying to figure out a way of capturing all of infinity into a finite space. This is if you lived in it and you could see out into that full area. So you're actually seeing those itty-bitty, tiny little figurines around the edges of space, but you're seeing them the way that you would see them if you lived there. You're seeing them as these real three-dimensional physical objects, and that's what makes it really feel like you're looking into infinity. You've got depth cues, you've got spatial cues, whereas for Escher, it's just trying to get it all into taking all of infinity and putting it in a finite space. Thank you.
We have a question over here.
Hi. So I was wondering, when you actually wrote the software for these negative curve spaces, does it just extend indefinitely and it just keeps rendering, or is these complete spaces that wrap around, with the sphere?
That's a great question. So we did actually do it as spaces that wrap around. So you're really inside a single cube, and then we've drawn it so that it looks like you can see that cube for some step-size distance, like translational distance away from you. But as you walk through the cube, once you pass the window, you teleport back to where you started, and we've got some code that changes the colors, so it makes it look like it's continuous. So that's why you're seeing some things flickering in and out.
That's cool.
Wait, one over here.
I can think of a few practical applications of this on my own, but I was wondering if you could tell us what some practical applications that I might not be able to think of on my own would be.
So, I mean, there's a ton of practical applications of virtual reality in general. So we were really interested in this sort of connection between these mathematical spaces and our spatial perception. So it's sort of interesting that we have all of these cues that are sort of built into our existence. Like we know that as something moves away, it's going to get linearly smaller. But trying to adapt to spaces where you can move your head around and things spin, it's sort of an interesting way of looking at perception and how you deal with that. My grad student, Brian, who's kindly helping out with the microphone, his PhD project is to make a game engine that runs in here. So you can not just walk around in the space, but you can interact with, like you could play tennis in the space, or you can sort of move around or do different activities.
Thank you, that'd be really cool.
Hi. So given that when you turn 90 degrees, your inner ear knows you're turning 90 degrees, but visually you're not turning the whole 90 degrees, does it get nauseating? Like, is that comfortable? Is it okay?
Actually doesn't get nauseating. So it turns out that there's two reasons why it doesn't. So one is that I have the state-of-the-art equipment and I'm running it on a GTX 1080 so that the refresh rate is 120 frames a second. And so any tiny motion of my head is getting tracked before my brain can detect that there's a problem. The other answer to your question, which is the geometrical answer, is that it is true that angles move differently, but there's a theorem in differential geometry that says that if you get a small enough patch of curved space, it's always going to look Euclidean. So centered at your head, it basically seems Euclidean to you. So moving a tiny amount, it's imperceptible very close to your head, but far away from your head, there's a large difference. So that's something that your brain kind of copes with. I mean, you can try it afterwards, and I've not had anyone say that they've been nauseated. I've had a couple people who have balance problems really feel the vertigo in the first one, but not nausea. And I've probably had 1,000 people through this, so.
That was a great talk.
Thank you.
I'm really curious. One of your volunteers, you asked, which way did it get bigger in? So, how do these spaces change communicating discovery? Like, if somebody's in these virtual spaces, how do you communicate what you're seeing and actually get potential insight when you start looking at these these weird projections of space?
So a lot of the best thing about, in particular, the HTC Vive is that you're really using your body. You are navigating using proprioception. You know where your sort of hands are, you know where your body is, and you know how your body interacts with this space. You can kind of use what you see and sort of try to describe it in terms, we only know Euclidean terms. We don't have a language for, mathematicians have a language for us, but as sort of physical beings, we don't have a language for how our interactions would change.
Gestures are great.
So gestures are great. Trying to do very controlled motion, like moving your head in a circle is something you can control, and moving your head in a big circle or a small circle, you can sort of change that, and you're sort of using the scientific method to explore how simple motions change how you're seeing things. Thank you.
Question over here.
So I gather you were telling us any set of triangles, like less than 6 triangles on a vertices is going to create a Euclidean space, and if it's more than that, it's going to become flat or ruffled?
So less than 6 is going to be a spherical space, So like an icosahedron, like it's sort of a closed spherical shape. Exactly 6 is flat, and more than 6 is ruffled in this hyperbolic space.
Okay. Just check, making sure.
One over here.
Now, is this related to fractals in some way? I'm just curious.
So fractals have this notion of being self-similar, but self-similar on different scales. So I have, a triangle like this, and I take that and put it over here, and then each of those I put it over there. So it's self-similar at different scales. This is self-similar at the same scale, but because of how the optics play tricks on you, it really looks fractal, and like you are seeing a larger and larger number of squares or triangles or rooms or whatever as you go further out. So that gives you sort of the illusion that it's fractal. But you could also say like, well, I don't really care that this is three-dimensional. All I care about is that 2D image. And so you could use this to create a sort of fractal pattern in 2D.
Oh, yeah, thanks a lot for the great talk. The phenomenon in which someone does the hula hoop and then ends up having turned, is this analogous to a Berry phase that people talk about in quantum mechanics? Or?
That's a great question. So yes, it is. So Berry's phases are called geometric phases precisely because when you go around, you're sort of measuring something about having gone entirely around in a circle. It turns out that to think about that, you have to think about slightly different space than Euclidean space. You have to get that curvature basically coming from the energetics of the quantum mechanics. So you are seeing that notion. It's just that the curved space isn't directly in front of you. It's a little bit more subtle.
And just
That's
the
a
last
great
one.
question.
Also, why didn't we see it in 2D when you only have the hyperbolic space in 2
So
dimension?
you do see some of it in 2D. So you can try it out. So the hula hoop one, you will see things rotate around, but the other ones you're not going to see, and that's because the two directions, the hyperbolic direction and the Euclidean direction, commute. So I'm not going to pick up any phase between them.
One over here.
Hi, so what are the applications of the hyperbolic plane? Like, how is it being used today, or where is it being used?
Okay, so this is sort of an interesting question. So you do see some of these notions in biology. There's reasons why you might want to create things that have very large surface areas and things like that. And we know you can't fit all of this entire space into our Euclidean space. So what biology does is it sort of makes an approximation. So it gets like as close to this as possible and then takes it and repeats it in these spatial chunks that can fill Euclidean space. So that's something that is very common in like lipid membranes and all sorts of sort of growth patterns. You can imagine doing this as a way of using this space as a way to understand really complicated data structures, things that have nested folders in them. And instead of remembering this weird linear path through space, you can have this zoom feature. So you can look at all of the network connectivity and move back and forth between it as sort of a top-down spatial view. So that's sort of on the UI side. You could also imagine if you can create these structures that have really high surface area, you could get better data storage per unit volume. So you're not stuck with, layered 2D systems. You could sort of use the curvature of these spaces to get a higher density of bits.
What kind of materials are you making this like geometry?
So we have been studying some of these minimal surface models. So one of my students who's not here today has studied a way of making a chiral minimal surface. So for that, we've only currently 3D printed it. The idea is that if you put it down to sub-micron scales, you get features that are about the size of a wavelength of light, and you can use that to control photonic properties in detail. So.
How about one last question, and then maybe if you still have questions, you can come down to the front. That way we have a little bit of time for people to play around. Was there another question over here? Or?
Do you have a question over there?
In the back, I think, over here.
Hello. I was just wondering, this might be a dumb question, but why does this only work with triangles? Like, could you make a non-Euclidean space with like squares or other types of shapes?
Absolutely. It doesn't just work with triangles, it works with any geometry. So that dress I showed at the beginning, that was made out of hexagons and heptagons and pentagons. That's just using the idea that you want to either add a little bit of area or take a little bit of area away. So basically, anytime you're sort of changing that, you're inducing curvature. But it doesn't have to be a tiling. It doesn't have to be regular. It doesn't have to be anything. So that's how these curved patterns in clothes work too. Is instead of having these sharp corners, it sort of spreads that wedge out over a longer period. That's how sort of princess seams work.
So you could like tell people that like you're wearing like a non-Euclidean skirt or something?
Absolutely. I am wearing a non-Euclidean skirt.
Okay, thanks.
Thank you. All right, thank you everyone so much for coming by, and please feel free to come up and play with VR.